Everyone, so welcome to today's session. So we're very lucky to have a double joint session today by actually Tucci and then Carl Janssen. So we'll take maybe a little 5-minute break in between the two on the switch. There'll also be a photographer from SwissMAP who will be coming today, taking some pictures of the conference. So just in case you see some paparazzi around, let them keep their camera for the day. Okay, thank you very much.
So today I wanted to talk about quantum computing with an eye on what can be done today with the data that are already available. So the plan is that so I would like to review all the basic ingredients to make sure we are all on the same page. Then I will introduce a class of algorithms that people use today on the machines that we have. And then Carl will come in and then he will talk about the applications for lattice-based fields.
No, I'm only here to close the windows.
Just press once.
I'm more active.
You need to press once.
No, it's not.
You think it's too noisy? Maybe like this is fine, so that.
Just press once.
Sorry.
Okay. So, starting from the start. So, with quantum computing, we mean a class of algorithms and hardware on which these algorithms can run, which leverage the principle of quantum mechanics. So, in particular, the superposition principle and entanglement. So, these are smaller or faster versions of an ordinary computer, but they're meant, in principle, to work in a completely different way. Still, this does not mean that quantum computers can compute things that are uncomputable on a classical computer, but they might be better at computing certain things. And this is what it means when people expect to see some quantum advantage or a speed up for specific problems. And there is a picture of a superconducting quantum computer. Yes. What is interesting about this picture is that the computer is actually just this tiny thing here, and all the rest are fridges that are needed to bring the computing unit to around 15 millikelvin, and the rest is connectors that are used to manipulate the units. Okay. Then get into the classes of problems that quantum computers might be useful. I guess for this audience, the most interesting thing is the quantum simulations. So the fact that a quantum system might be good at simulating another quantum system. And this is relevant, of course, for lattice field theory, in quantum chemistry, material science, many body physics, among other things. But here there are, instead there are classes like classical problems, where also quantum computer is expected to be useful, and famously the problem of factoring, a number that is the product of two prime numbers. But we have also searching algorithms, as finding a specific item in an unstructured database is something that is difficult classically, but quantum computing is expected to help there. And also in optimization problems, like combinatorial optimization problems is something that people look at. And to finish, of course, people think about applying this in machine learning, like in, boosting machine learning with quantum processing units. And then, of course, we have the entire field of people. Now, going a bit more towards actually computing, I wanted to mention that quantum computing is more like a framework. So quantum computing can mean different things. And here, top left, we see the circuit-based quantum computing. So this is maybe what is more like intuitive, because it's classical, like it's closer to how we think maybe of classical computing. And so it's the computing meant in terms of wires and gates. Whereas down there we see quantum simulators, where instead one uses a quantum system that evolves according to an Hamiltonian, which is a model for another quantum system. So by studying then this first system that one has available, can learn things about the model from the other system.
What is conceptual difference between the two? Is it because one is like continuous time evolution and the other you think more of discrete time steps? Because circuit is some it's some quantum system, no? So like why? I'm not sure I understand what is the distinction.
The first thing is that this is supposed to be universal and this not. So this, depending on which gate you use, you can do any computation. In the other case, instead you take a system, this will represent one specific model and you will study this. Okay, so then of course you need to change the system than to change the model. This is the first thing. The other thing is that basically when you practice, you will want to realize certain gates. Physically with the device, you will want to be able to do gates and you will put this in a series. Whereas in the other case, you have more of a analog computation, if this makes sense. Mm-hmm. Okay. Whereas instead, so measurement-based quantum computation instead is something that is analogous to circuit-based quantum computing. Like they're equivalent, or just different descriptions. And this program, based on measurements, comes from the idea that in quantum mechanics, if I measure a system, I also manipulate it. Like I also induce a modification of the system like this. So instead of having active gates, one can also just think of performing a computation by measuring the system. And last, we have adiabatic quantum computing and quantum annealers. Where here, so what we think about adiabatic quantum computing in the following way. So we have some Hamiltonian, we want to find its ground state. This might be very complicated Hamiltonian. And so where we start is from another Hamiltonian, which is very simple. We know what the ground state is, and we know how to put our quantum device on the state. And then we very slowly deform the Hamiltonian from the first easy one to the difficult one. If we do this in an adiabatic way, so slowly, there is high chance that the state, the system which was in the ground state, keeps staying in the ground state. So at the end of the computation, we have found the ground state we were after. I hope it's okay. And so quantum annealers are a specific class of non-universal computers that are based on this principle, and they are used specifically for classical optimization problems. And I mentioned this because it's also quite mature kind of technology. Like, now, if you want to.
So the idea of this last thing is that you can design some Hamiltonian whose ground state would correspond to solving some classical optimization problem.
Yes. So talking about today, we are in what is called the NISQ era, meaning that we have quantum computers already, but they are noisy, intermediate scale quantum computers. So we have machines with the order of 100 qubits. They are noisy, and this limits the circuit depth, so the number of operations we can do on these computers, and there is no error correction. But there are claims that quantum computers already have outperformed classical computers, and in some sense. But the point is that also that soon we will have better devices larger devices with better qubits. So it's an interesting place to be. Now, what I will do next is then to go in the details of the circuit model of quantum computing, so review all the basics of the ingredients, and then go on and talk about the 3-bit quantum classical algorithm that people use today. Okay. So, in quantum computing, the fundamental building block where information is stored is the quantum bit. The qubit, which is nothing but a two-dimensional quantum system. As such, a state is described by a vector in a two-dimensional Hilbert space, which we can take. For which we can take a basis, which we call 0 and 1, and this is called, in this context, computational basis. And of course, an arbitrary state can be a generic superposition of these two states. And it's typical also in the context of computing to represent this as a ray of the block sphere using this 2, 1, and 5. And of course, then let's say this in classical computer, we had the bit only, and this is a binary variable, it can be 0 or 1. So the bit only sees the north and the south pole, whereas on the qubit, we can explore the entire sphere. But of course, when we get from a measurement, it's only the 0 or 1 in a probabilistic way. Okay. If we now have n qubits, the Hilbert space will be the tensor product of n single qubit Hilbert spaces. This means we will have 2 to the n basis states. So a generic state then, in this case, will be written in the following way with 2 to the n coefficients. And of course, qubits can be entangled or in separable states. And this is important because the key here is the possibility of having entanglement. Because if we have n qubits, but they are in a product state, so we need 2 numbers to describe each qubit, so we have 2 times n variables. Whereas if we have an entanglement, so generic state, we have 2 to the n, we need 2 to the n numbers to describe it. So we access a much larger, it's just the entire Hilbert space in this way. I'm so familiar with this, but we use this notation where normally one names the basis space like this, where x is the binary representation of the number. Okay. Now, we have the qubits, we want to manipulate them. We do them through quantum gates. So, of course, in this context, a state will undergo a unitary evolution under some Hamiltonian. So these quantum gates are unitary matrices. And they act typically only on a few qubits at the same time in a non-trivial way. So regarding single qubit gates, these are some examples that are in fact the most important examples. As we see here, X, Y, Z are the quantum gates which correspond to the Pauli matrices. The X in particular is the quantum version of the NOT gate, so this flips the qubits. And this was the only thing we could do in classical computing with one gate, with one bit. And I said here there's richer class of transformations. And one gate that also is important and widely used is the Hadamard gate. And this is because this gate can put the state in a superposition state. So from a computational basis state 0 and 1, we get to the plus and minus states, which are superpositions, equal superpositions. And of course, these are the eigenstates of the X operator, so this is also the change of basis.
What in classical computing we cannot do, for example, the set operation? I understand that usually we do the X operation, so if we are on or off, right? But why we cannot do the set or the Y operation?
Okay. This will not really, an overall phase will really not make
will not make sense.
Yeah, will not have an effect.
Okay.
Right? 0, 1, 2, 3, 0, 1.
Okay, so you are saying the set is doing an overall phase, the A2 pi there,
Yes.
and the Y is doing.
Yeah, and the single state is doing some overall phase. You need to have a superposition which you don't have. Or another way, I don't know what to say. We have 0, 1, we don't have minus 1. That's right, we are going out of outside the realm where we should stay, I don't know how to say. Yeah. Okay. Looking at these operations in terms of the block sphere, of course, with the x, y, and z metrics, we can generate all the rotation around all of the axes. So we can do all of we can get to any point of the block sphere, to any other point. So we can do all of the single qubit rotations. Okay. So we move on to control operations. So operations of the type if A, then to B. And these are gates that act on at least 2 qubits. One of which is the control qubit, and the other one is the target. And the C0 is, of course, it's a famous example. It can be sort of a generalization of the classical XOR gate. If you're not familiar with this, it will be better. This is how the C0 is represented graphically on the circuit, and this is the matrix that corresponds to it. And what it does is that it flips the target qubit if the control is in the state 1. So here, if this is the first qubit is the control, the second one is the target. So nothing will happen to this state and this state because the control is in 0 state. Whereas here, the target qubit will be flipped. So it's a control node. This operation is important because we can use it to create entanglement, to entangle states. So, in this situation here, we start with this product state of +0. This we can write like this, computing the tensor product. And so nothing will happen to this state if we apply a C0, but in this case, the 0 will become a 1, and so we end up with the state there, which is a Bell state. So it's an entangled state. So with this kind of, in this sense, we can say this C0 can create entanglement, and for this reason, it's so important for quantum computing. Actually, this is the only multi-qubit gate which is really essential. So actually, the treatment of gates can end here, but I just wanted to mention a couple more of examples for completeness, and that is that. So control operation can be done also with general transformations. Doesn't need to be necessarily a NOT or X. Another thing that we can do is that we can swap the state of 2 qubits with this gate. This is important more when thinking about the hardware, because maybe we want to do an operation on qubit 1 and qubit 10, but they are far away, and so we need to swap the qubits until we get them close to each other, and so this is why we need this swap gate. And the Toffoli gate is a controlled NOT. So there is 2 control, like it's the C0, but the C0 will happen only if the first qubit is in state 1. And this I mentioned because this gate for the classical version of this gate is a universal gate. So all of the classical computations can be done with this gate alone. And since we can do this also on a quantum computer, this means we can do with a quantum computer the simulations that the computations that a classical computer can do. Okay.
Is it how many gates are there? Because now here you mentioned 2 that I never heard about.
Okay.
But is there a finite number of gates, or you can keep on inventing things?
So the gates are all of the possible unitaries.
These are all the possible ones.
No, I'm saying you can have
all
of
the
the
possible
possible
unitary
unitaries, right? Then I get to there in a moment. Like what is relevant, of course, is let's say, so the gates are all of the unitaries. When in practice you realize a computer, maybe you don't want to have to be able to implement all of them. You might want to have a set of them that is universal so that you can create all of the unitaries with them. So for example, the swap gate can be reconstructed with C0 and single qubit gate, right? Toffoli also. So that's why I meant that this slide, sorry.
This is, as you said, right? It's a CC node, right? So
exactly. So I mean, there are universal sets, and then the others can be reconstructed. Then maybe there is this company. They have this quantum machine, and for them, the swap gate is really native operation they can do on qubits. So in this case, they might take this as a fundamental building block and try to reproduce the C0 combine. So this depends on actually how the hardware is done. Okay. Now going into quantum circuits, so combining multiple gates and measurements, we can build circuits, which are read from left to right. It's typical to start with all the qubits in the computational basis. So this state will be a product, tensor product of these three zeros. And then applies this to them. So the depth of the circuit is the maximum length of a directed path from input to output. So 1, 2, 3, 4 here. And to extract information, we measure the qubits at the end. So this is the symbol for measurement. After the measurement, we have one bit of classical information, and this is represented by this double line. It's classical information, whereas the line is quantum information in the qubit. And then we go back to what was asked before, that so a set of gates is universal if by computing gates from them, one can approximate any unitary transformation on any number of qubits to any desired precision. This is an approximate definition of universality. And there are different classes that one can take. And maybe first interesting is this, that with the C0 and single qubit rotations, one can represent any unitary. This is an exact decomposition that one can do. But of course, these are continuously infinitely many gates, okay? But if one is happy with the approximate definition, one can use, for example, this set. These are just 3 gates. So one needs to be able to implement these 3 gates on hardware, and then can in principle do any unitary.
The H is Adam.
Yes. Yes. So in principle, here now we know how to do any computation on a quantum computer. Okay. So at least then putting the things together, at least in principle, why is the quantum computer is supposed to be more powerful in certain cases? And the first point is that when we have n qubits, the number of basis states grows exponentially. So we have access to exponentially much more memory at little effort. Like it's difficult for a classical computer to simulate just 2 to the n functions that are needed to describe a state. And this instead is easy in this situation. But then, of course, we also have superposition of basis states, and we can apply unitary gates to these superpositions. And this leads to what is known as quantum parallelism. So we can compute various things at the same time. And of course, then the various branches of the superposition can interfere, and the entire point of the quantum computation is to make them interfere in such a way that interference is disruptive for wrong answers to the question and is constructive for correct answers. This is how one should design quantum algorithms. And then lastly, qubits can be entangled, and this is correlation that happen in classical algorithms. So in principle, we're putting in completely new ingredients. Okay. For now, I would like to go into like what really one can do now, like today, meaning, yes.
Is there anywhere that we can actually prove that there's no classical algorithm that could be as fast as the quantum one with an exponential speed-up difference?
Okay. Can you repeat?
Yeah. Is there any example where we can prove that there's no classical algorithm that could ever do as well as a quantum one with an exponential speed-up?
No, I don't think so. Yeah.
The best is like Grover with like quadratic
No, I mean there is for the Shor's algorithm for factorization. There you get exponential speed up.
Yeah, but can you prove that there's no?
Exactly, that's the point. That this exponential with respect to the best classical algorithm known now. But every year there is a better version of classical computing. So it's really not clear. I mean, it might be that at some point we realize that there is no advantage, right? I mean, there's also a lot of evidence, but yeah.
I think there are some papers by Ignatius Sirac where he showed that under certain conditions there is no classical algorithm that can beat the quantum algorithm. So there are cases under certain conditions where the classical computations cannot beat the quantum. I don't have the conditions on top of my head, but there are papers like this.
But the question that sometimes it's interesting, it's like I don't know what examples you refer to can be, but I think it's interesting that when I heard this discussion of like, I mean, we don't have so many situations where we know a good quantum algorithm. We really have exponential advantage. And so when we do have, it's because there is some structure there, and we make use of the structure. And then, but this is a special problem, and maybe precisely because they have the structure, maybe one day we can do a good classical algorithm. Right? So that's why I don't know what, because maybe there are problems for which classical good algorithm will never exist. Will then a quantum good algorithm exist? Like, I don't know. I just think that yes, I guess it's not. Okay, but so instead of going to this like very nice like fancy algorithms, we go into what people do today, which is something much simpler. And this is because we have these NISQ devices, which are small or intermediate scale. They have a lot of noise. Depending on the technology, one might have a lot of connectivity between qubits, low coherence time, low gate fidelity. This depends on the specific technology.
Sorry, what do you mean by connectivity?
I mean that really how much you can connect one qubit to each other. Like let's say the topology of how you put the qubits. You have 10 qubits. Are they in a row, and so the first just talk to the second, or they are like how much they can talk to each other.
That the gates can apply to any pair? That's
also, exactly. Like if two qubits are far, I cannot directly apply a gate to them. I need to do something in the next. And this is very important, actually, because one normally really thinks of how many qubits there are, but it really matters how they are arranged. So the possibility of freely deciding how to arrange them is very important. And this is actually one of the nice points of neutral atoms. One can move the atoms around, and so one can change the connectivity according to the need. Whereas for a superconducting quantum computer, this is fixed. So in general, now only shallow circuits can be executed. So if we really wanted to solve some useful problems, we will need large number of qubits, grid circuits, error correction. So really now what people do is proof of principle demonstration. Okay, so we're here, we want to do that. But the question is, how can we use this existing hardware in a beneficial way? And so from this question comes this idea of quantum classical algorithms, where the idea is to combine classical and quantum devices, and to rely on classical computing where possible. So we use the quantum device as a coprocessor. So this will be a processing unit which is tackle the classically hard part of the problem. And then feed the classical data obtained from a measurement back to the classical computer, which will do the rest of the computation. And this way, basically the quantum device is a booster for like the classical computer, and maybe even a modest quantum hardware can give an advantage. So more in practice, we talk about variational quantum classical algorithms, where one focuses on minimization problems, so where one tries to minimize some cost function, cost function is a function of some parameters, so and it is computed as the expectation value of some operator over a parametric circuit. So we will solve this problem iteratively using parametric ansatz. So the quantum device will prepare this variational ansatz and compute the expectation value. This will be given to the quantum computer, to the classical computer, which then has an optimizer which will find the new parameters. And this will go on in a feedback loop between the classical and quantum device until one reaches convergence. Why do we want to do this? Well, because a large class of problems is naturally in this form or can be recast in such a form. Because so optimization problems, one might think of them in terms of minimizing some given function. Machine learning, of course, but also in physics or chemistry, one might want to find the ground state of a Hamiltonian and things like this. And evaluating these expectation values is in general exponentially costly in a classical computer. So if the ansatz is expressive enough, and so if the optimization worked, at the end of the computation, the cost function will, of course, correspond to the smallest eigenvalue of the Hamiltonian, of h, and then we will have this theta, right, for preparing the state, and this state will be the ground state of the Hamiltonian.
Sorry, on classical computer is evaluating this. I had before. Yeah, evaluating this psi h psi is exponentially costly in the size of the. Not in the dimensionality of the basis, right? It's in the size of the Hilbert space. This is exponentially in what? Yeah.
Yeah, in the size of the problem. It was still this thing of like, if we have n dimensional state, like if we have n qubits, we will have 2 to the n states. Right? And so we need to write, in principle, yeah, so we will need to keep track of these 2 to the n functions. And compute the expectation.
Because evaluating for given theta, it's easy to evaluate, right? You just compute the multiply matrix and a vector. But you say you have 2 to the n.
Yeah, I mean a generic state will be. The thetas are not 2 to the n. That's the point also, right? The parametric circuit, I decide how many operations I do. If I do 3 operations, I have 3 thetas. Right?
But so it's linear in the number of thetas, right? Am I understanding correctly? That it's just you need kind of exponentially many thetas to find a good.
So this is an example of a circuit. So in this case, for example, there are 8 angles, but we have 4 qubits, so it's 2 to the 4. I decide, for example, to use 8 rotations, so 8 thetas. So these two quantities are not directly related. This depends on how I decide to do the parametric circuit. So it's up to me to decide this ansatz. Then of course there are better or worse choices, but it's not strictly related to the dimensionality of the space.
So you're running your quantum computer with some given thetas, right? Like once, let's see one run, and then you just get one data point. No, you get this psi h psi for this given choice of 8 thetas.
Yes.
Right?
Yes. Then I compute this expectation value on this theta that I just prepared with this theta. And this will be some number. This will be given to the classical computer and a classical optimizer.
Yeah. I guess I'm confused. Why is it complicated on a classical computer to So I understand that quantum computer does this at once, okay? So for given status, but also classical computer. You say for classical, why is it complicated for a classical computer to do this operation for given thetas? It's just you have a matrix because it's like a big matrix.
It's a big matrix. This is that point.
Okay.
That for n qubits we have a 2 to the n times 2 to the n matrix. When n gets large, this becomes simply costly.
Okay.
That's the point. It's not much more than this, honestly, in my opinion. But this is something that can make that matters in practice.
Sorry, one more question. Like on the quantum device, you compute something like at a given theta, and also small steps around it to know
Yeah,
that.
to be able to. I mean, this depends also on how the optimizer works. But maybe something like this: you have a theta plus epsilon minus epsilon. You compute the difference. You understand in which direction to go. Something like this. Yes. Okay. Okay, so this way of computing things, when we want to really measure an n-cubic Hamiltonian, goes under the name of variational quantum eigensolver. And the way to implement this is to take our Hamiltonian, write it as a sum of Pauli terms, which is something that can always be done. So, of course, in principle, this are now exponentially many terms. So the exponentially many we now got shifted somewhere else. So this means in general this will not be an efficient thing to do. This is only nice and efficient if there's actually not exponentially many, not zero coefficients. Otherwise we didn't gain anything. We shifted the problem somewhere else. But for like physically interesting Hamiltonians, this is the case. Then the cost function will be given by the sum of all these expectation values. So in fact, this is what the quantum computer will compute, the expectation value of these value operators. Yeah, and this is efficient as long as there is only a polynomial in n terms in the sum. Okay. In principle, then one can extend this to excited states. Once we have the ground state, we can compute the first excited state and so on. And this is done by adding a penalty term like this to the cost function. So that we'll have an effective Hamiltonian, for which now the ground state looks like an expensive state. We added this term, which is the projection along the direction of the state we want to exclude. Okay. Yeah, so it has to be large enough so that, the normal degree will find this state. But with this penalty now, the state is there, so in principle, this algorithm will now select this orange state. That's the principle, if everything works. But of course, one needs to input this beta. Okay, so to go, so I wanted to show an example where how one actually does this. So I will first go back to something more basic to get in practice to what people do. And so I will to discuss now how to measure observables on a quantum computer. So let's say we want to compute this expectation value here of operator O on state psi. So this actually what we will compute in fact is this. Oh, sorry, maybe this is only interesting in this situation because we can only measure zeros and ones, right? We can only measure on computational basis. So the question is, what does it mean to measure a generic operator? Okay. So what we do then is to take this operator and diagonalize it. So this will look like this in the computational basis. So these are can be written like this as projectors in the computational basis. So
sorry, just to be sure, big N is the same as little n from before, or is it a different thing?
Yes, it's the same as little n. Yes, sorry, there is no. Okay, so yeah, so this U matrix now is this change of basis matrix. We insert it here as the identity, and then we think of this U as acting on the state psi to get us psi prime. And so then finally we are here, and this is what we want to compute, where this D is diagonal now in the computational basis. So also this the psi prime state, which now got, we think of it as expand in these terms as expanded in the computational basis. It will have some coefficients. So really what happens is that we want to compute this, but we in practice compute this, but in practice actually really this is what is happening. And so the expectation value is just given by the sum of the eigenvalues weighted with the modulo square of the coefficient describing the state. And so this is what the quantum computer is giving us. And this sum is classical processing. Yeah, so this matrix U is called often post-rotation, and as I said, instead of measuring psi, we measure psi prime. In fact, we measure this probability distribution, the various coefficients. Yes?
So a couple of questions, just to unify, or the last two slides, because in the last one you were saying you can not only measure a minimum, but if you're clever, you can measure some excited state by putting an extra term. Mm-hmm. And now, what is this claim about? It's about the details of how you compute the expectation value of an observable state?
Yes.
And so you need to diagonalize it. Is it a practicality remark of how you do it, the details, or is it... I'm not sure what I'm supposed to be getting right now.
Yes, so maybe in a second I go to an example, maybe you understand, it's clear what I mean, but the point of this slide is like, once I have a device, I can really only measure in computational basis, meaning like on the Z, expectation value, like really I can measure the eigenvalues of Z, so this is for one. What if I want to measure the expectation value of X?
Some observe X being sigma X direction or something, or
X, exactly. I'm saying some other, or like some
some observable.
So still the quantum computer will give me only zeros and ones. So this was just to say then, sorry.
It's about how to encode the expectation value in the output, I suppose. Given that the output is only zeros and ones.
It's also about how you construct the circuit, because you wanted the state, so you would say maybe I need to write a circuit that prepares the states. What I'm telling you is that actually you need to prepare this other state. So you need to add a part of the circuit which will do this rotation for you. And then we will measure the zeros and ones, and then you will get this, and then you can do the sum, and finally get the expectation value you wanted.
Still not fully clear, but maybe you said there's an example later.
I will exactly do this example, and maybe this becomes clear. So here, let's say we want to, we're interested in the state psi. This is 0 rotated by pi 4 around the y-axis, and we're interested in the observable x, sigma x, and we want to compute the expectation value of this operator on the state. So now this sigma x is not diagonal in compositional basis. It's anti-diagonal. We need to diagonalize it. How do we do it? The ease in this case is done with the Adamar gate. Okay, so this is the change, the diagonalizing method. And this will give us Z, actually, in fact. So talking about this, and the eigenvalues here in this case are just 1 and minus 1. Okay, so then again, regarding the post-rotation, so the state psi prime now will be given by U acting on psi. In this case, our U is the Adamar gate. Okay, so we end up with a circuit like this. So if you want to measure the expectation value of X around this on this state, what we need to do is to prepare the state, but then rotate it with H. Then we will measure in computational basis. Okay, So, and what we'll get is something like this. So actually, so here blue is the theoretical result for how many times we should expect 0 and 1 state. And this is how then we compute the expectation value. It's like weighting the eigenvalues with this coefficients. So in this case, these are 1 and minus 1. So this expectation value is simply this minus this. Right. So this is the entire point of the previous slide. I think it's clear.
I think I'm so is the diagonalization like a pre-processing step here?
Yes.
Is that not then I thought like if you diagonalize the Hamiltonian, or the operator you want to do, you would have done anyway, right? I mean, if you know the matrix to diagonalize it with, or why? I mean, if you have to classically diagonalize the operator before, what is then the advantage afterwards?
So you do. So the advantage is again in the is basically in the state preparation, in how you store the state. We're back to
I don't think I understand that.
I am also confused by what you're asking, yes. Because it seems like you told us we need to somehow know how to diagonalize the operator, that is some complicated operator in principle. But then we kind of want to measure its eigenvalues, roughly speaking. That's how it looks like to me now.
But it's not quite like this. So the first thing is this makes sense only when the terms in the Hamiltonian really act on only a few qubits. So you need to diagonalize a matrix, true, but this will be a 2 by 2, like a 4 by 4 matrix, right? And the rest of the Hamiltonian, the rest is acts trivially. So these matrices we need to diagonalize are easy. And then we know the eigenvalues. Now the question that is relevant here is we want to compute the expectation value of some state. Of this Hamiltonian on some state. And then what is difficult for the classical computer is to represent the state. We need 2 to the n numbers to represent the state. Okay? And so then the quantum computer, this is what it's doing easily. Writing down this generic state and giving us just to basically the probability of getting 0 or 1. And with this we can reconstruct then value since we have diagonalized the matrix.
And you do?
No, I just wanted to say that it's true that maybe there is more classical post-processing than one expects at first when you look at quantum computing. But that's the point of this hybrid classical quantum algorithms, that's to really also use this power. Sorry.
And then for the given state, you just do one measurement and that gives you the expectation value, or you need to do some repeated measurements to get this individual probability.
Yeah, so you need to do many. So this was also the meaning of this slide. We expect this blue, but we get this orange if we do like around 100 shots. So we repeat this circuit 100 times, and any time we measure what we get, 0 or 1, and then we get these frequencies. So these are very off. And in fact, the expectation value is also very wrong. And only when we get many, we get to convergence. So the error is going like 1 over the square root of 200 shots. You need to analyze the matrix, understand what state to prepare. You prepare it, you run it, and you measure it many times, and then you get these frequencies, and then you get your expectation value. Yeah. This is the procedure. Okay.
So sorry, now with this you have extracted the CX primes from the first slide.
Yes.
Okay.
Yeah, and in this case, then the expectation value, since the eigenvalues are 1 and minus 1, was just C0 squared minus C1 squared. And this is what this is. C0 squared, C1 squared, and this is the difference. Okay. So given that we know how to compute these expectation values now, let's look at an illustrative example, which is we can look at the ground state of the transverse field easing model. Just this Hamiltonian that you see there. So this is already Pauli matrices. And what we expect to see, if we look at the ground state, there's a phase transition from an ordered to a disordered phase as we increase h. This means, so if h is 0, our VQE should find as the ground state the product state of all zeros, so all spins align in the direction, or all ones actually, there's two degenerate states. But if h is large, then VQE should find a ground state which is the product state of pluses. So all spins align in the x direction. Then how this is done? So first of all, maybe one has a little penalty term to distinguish between the two degenerate states at h equals 0. And then we do this with VQE. So it's the procedure we've seen before. So this is the quantum processing unit. So we prepare the states, the qubits in the 0 state, and we apply some parametric circuit. In this case, this is the circuit. And this is something typical. It's called the hardware efficient ansatz from IBM. And this is called hardware efficient because it's an ansatz that is efficient for the IBM quantum computer to realize on the IBM hardware. And the structure is that one has entangling layers with C-naughts and layers with single qubit rotations. And the thetas are now in these rotations. And then one takes this ansatz and one can, for example, decide how many times one repeats it, so how many layers. Okay, so in this case, was done for 2 layers. So this is the parametric circuit. Then we need to measure the qubit. Maybe first here we have these rotations. These were the rotations that we were discussing this slide before to compute expectation values of operators that are not just that. So this will be then the quantum processing unit. This will give us the expectation value. Actually, of all of these individual terms, then we need to sum all of them. We can also do this in parallel in here. So that's also nice. It's also an advantage. And then this will be given to the optimizer, which will find new thetas, and then so on, until we find the ground state.
Where did you put in Ising Hamiltonian in this quantum computer?
Here and nowhere. No. This is literally computing the expectation value. Maybe this is wrong. I mean, it's misleading. Like, this is the expectation value of every single term in the sum. So I prepare this state, and it's compute the expectation value of all these terms. And then the Hamiltonian, the expectation value of the Hamiltonian will be given by the sum. So I don't actually construct the entire Hamiltonian, but only the individual.
Yeah, okay, then where do I see that the individual terms are the Ising ones?
Yeah, okay, so sorry. This was like, so the individual terms I'm computing, but so this, the circuit is this what you see. So there is no Ising model here. So what there is, so the Ising model I will see because I calculate here. So the expectation value of this will be the expectation value of 0, x1, and so on. So this Hamiltonian exists only as a measurement. This is what, right? And so one thing that what could do is that, so in this case, this is an hardware efficient ansatz, meaning we choose the ansatz so that it will be easy to implement. But of course, maybe what would be interesting to do is to choose this ansatz so that it knows we're talking about the Ising model, right? So put some of the symmetries of the problem, like this is where one can play to let the computer know what is going on. But then maybe this will be difficult to implement on hardware. So one is maybe a long circuit. So it's a threshold there to.
Because I'm not seeing where, so let's look at the first term, zi times zi plus 1. And for fixed n, I know. There's some terms that is z3 times z4. At which point I am evaluating expectation value of Z3 times Z4, where is like, where, because this IBM gates or whatever, they are not, there is no term here that is exactly Z3 times Z4, right?
No. So it's what we had before that, so we need to take the Z3 times Z4 matrix, we need to diagonalize it,
Okay.
we know the eigenvalues, and then we have these coefficients
Okay.
of the various basis states which we get from measurement.
Okay.
We get these probabilities and we can
Mm-hmm.
You wanted to say something?
No, you said it, but maybe just to add, this is really the art. If you give me a Hamiltonian to design the quantum circuit that really have the chance to represent this Hamiltonian and give you a good answer, and there's no general recipe to do this. So this is really when we are sitting down and we are trying, I will show you different circuits that are much more complicated, and this is really where we sit down for weeks and months to find the quantum circuit that gives us good result for a given Hamiltonian. You can think of the quantum circuit as an effective Hamiltonian that represents the real one that you want to target.
Okay. So going on, these are results on a simulation of the quantum computation. So what we did is, again, through this process we found the ground state. At the ground state we can compute the excitation value of the magnetization, and this is plotted here. And so one sees this behavior that we expect as h increases. This goes from 1 to 0, and errors and state fidelity are reasonable for the simulation. But what I wanted to show is that if one puts it, this is for 4 spins actually. If one puts this on hardware, things start becoming a bit of a mess. In fact, here this is much less visible, but the point is that one can see the qualitative behavior. So this maybe is the, I think, in my opinion, like maybe also a bit of the state of the art, that one cannot do really precision measurement maybe today, but can see qualitative behavior. Okay. And so to finish, I would like to talk about something that has nothing to do with physics, but maybe can be of interest for you to know in what sense people try to look at problems that are not really related to spins with a quantum computer, and also maybe highlight what are the challenges. So this is the flight data assignment problem. So we have an airport, we have some flights, we want to assign them to gates in such a way that the passengers spend the least time in the airport. Okay. So we have a cost function that is the total time that passengers spend in the airport. This will be given by people leaving the airport, need to go from the gates outside, the taxi people that are arriving, and transfer people. Okay. We can think of this cost function as receiving contribution from associated with this binary variables, the 2 indices, I and alpha. Where I is the flight and alpha is the gate. So this variable will be 1 if flight I is assigned to gate alpha. Okay. And then with actual data from airport, or I don't know, one can compute this function. Okay. And of course we want to find the best solution, so the best combination of this variable such that this function is minimal. So this goes under the name of Kubo problems. So the first thing is that actually, so this is the cost function. But if one really wants to do this optimization, is to add some penalty terms, like some constraints, because there are some things that cannot happen. For example, one flight cannot be assigned to 2 gates. Doesn't make sense. Or 2 flights cannot be at the same gate if they are too close in time. Okay? There are some constraints, and so there's some penalty terms that try to say to the optimizer, like, these are bad solutions. Okay, so this is actually our full cost function, which can be written like this. So, and this form is called quadratic and constrained binary optimization of function. Yeah, and it's a kind of class of classically hard problem. So this is the problem we want to solve, and we want to do this with a quantum computer. So we, of course, need to have an encoding. So we need to have a way to encode this classical information of like whether a flight is assigned to some gate. We need to encode this in some qubit. So one way to do this is called so-called one-hot encoding. So really, we assign to each of these x variables a qubit. So this qubit will be instead 1 if the flight is assigned to this gate, or 0 otherwise. So we'll have then f times g qubits and to the f times g states. And then this Kubo cos function is mapped to an Hamiltonian in this way, where this mapping is ensuring that the encoding makes sense, like that really, when the expectation value of this on the qubit is 0 if this variable is 0, okay? And so then this Kubo Hamiltonian now became some sort of generalizing model, and this we can put on the quantum computer in the same way we saw before. And in fact, people from this paper have studied this in much of a similar way to what we saw before, so with these hardware efficient ansatz, and they got some results there. I think, but the point I want to make now is a bit different, which is that is the following. So out of this g variables, only one can be equal to 1. The others must be 0. Because these variables are I is the flight. So this variable will be gate. Flight I is assigned to the first gate, the second, or the third of the gate. So only one of this can be 1. The other must be 0. Okay. So there is a lot of redundancies here. Like we are wasting a lot of space. Like all these qubits, we can have the state 1, 0, 0, 0, but we cannot have 1, 1, or here, okay? So in a way, this encoding is very redundant. So there is a better one in terms of space, let's say, which is called binary encoding. In this case, one doesn't use g qubits for each flight, but only log g. And so there is then this advantage of like the amount of resources we use. And this goes like this. So since only one of this can be 1, we record which gate this flight is assigned to. And for this we need log g states. So for example, if we have 8 gates, and we assign the flight to gate 8, number 8, right? This will be state 1 and a lot of zeros. In this first way of writing this, in the second way of writing this, we want to then record the number 8, and for this we need log 8 qubits. So we need 3 qubits, and so 8 will be written then in the binary representation as 1, 1, 1. So what here was 8 qubits with only a 1 is now here 3 qubits with 3 1. If you lost me here, it's okay. I just want to mention really here that there can be different mappings, and different mapping can mean different use of memory and different efficiency, and can have different performances. So here the results from this paper, there they seem to see that the second encoding is better than the first. Is this solid line, but really, besides the results, here I want to pass the message that this is all active areas of research, like how really we encode data. This is true for classical problems, machine learning, but also for physics. How we encode the data into qubits matters, and people are studying what the thing to do is. Which type of circuit to use also matters. How many layers, there's, for example, different design for different layers of the same circuit. So all this is things that people are studying. Yeah. And so to conclude, this BQE can be good for computing ground state or low-lying excitations, and is efficient as the Hamiltonian only exists as a measurement and makes sense as long as h is only a polynomial number of terms. The entire point is that there is great freedom in choosing the circuit, and this then, depending on the situation, one can decide to do it prioritizing the problem requirements or the kind of hardware one has or the expressivity one wants to achieve. Those are all compromises one needs to make. Overall, this entire program has a problem that is called barren plateaus. And what is happening here is that if the circuit is very expressive, so if there are really many parameters and a lot of entanglement, what happens is that the landscape of the cost function starts becoming flat and the minimum starts becoming exponentially narrow. So, and then the optimization stops working. And so this is actually a problem that a lot of people are working on, trying to figure out what to do here. Okay. So, moving into the summary. What I hope I told you is that hybrid quantum classical algorithms are promising approaches for these devices. Barren plateaus seem a major challenge for the training process as we begin to scale up in size. There were being already the first successful proof of principle demonstrations up to around 100 qubits. Noise is currently the major limiting factor that prevents us from scaling up. So right now there is no quantum computer that is big enough or as good enough quality qubits to solve lattice field theory problems beyond what can be done classically. I guess in general to solve interesting problems beyond what can be done classically. But those roadmaps with better and more qubits really soon, and so I think this is interesting to see because really the scaling is impressive. Like every year this has really scaled up in an impressive way, so it is probably true that maybe in this decade or like the next decade we will have fault-tolerant quantum computers, 100,000 million qubits, or I mean this, considering how things have scaled, this can be actually the case. And then things start becoming different. But really in the next future, maybe next year or so, what people are implementing is like error mitigation techniques, so to make the calculations more precise. So for example here, maybe next year we will have some 1,000 qubits, but some of them will be used for this error mitigation. So one may still have the same number of operational qubits as this year, but they will be better because they're error mitigated. So then soon the size of the devices might be already big enough to do something big on the capabilities of classical computers for specific problems. But of course, if we want to compute with the state-of-the-art Monte Carlo simulations on lattices, we will need millions of qubits. Actually, millions of logical qubits. So logical compared to classical is like times 1,000 now. So 1,000 millions qubits. Okay. And this maybe it is the case in a decade or two. Or, I mean, it's also an evolving field, so maybe there will be breakthrough for which this number actually really scales down. And also this doesn't mean that one cannot do things interesting also to a smaller scale. For example, accessing routines which one can simply not look at in a classical way. So yes, so this is all exciting, I think. And that's where I finish. Carl will tell you more about the real application for physics. Thank you.
There is another method to minimization problems, which is with neural networks. So it kind of fully classical, but for layman looks a bit similar because you also have some ansatz, you parameterize it by some variables, and also this ansatz is usually, you act on some nearby states, but there so it's a classical thing, but there your functions are non-linear, right? Functions of somehow, and here it's more of a linear evolution because of. So is there any way to compare these two approaches? How this quantum thing is there any relation to this neural networks business?
So you mean neural network in general?
Yeah. For it seems like don't people apply neural networks to solving similar problems? And I mean, you kind of do you have some ansatz to parameterize whatever your answer, right? And then you do some gradient descent or whatever in the space of these parameters. But of course, functions that you produce have some different structure. But they're also built out of some small building pieces, as we do here. So is there any way to understand how the two are related?
I mean, I think in this sense, this is really analogous. Like what one wants to do is to have a cost function of some parameters. Then how you construct this function in this way would be through a quantum circuit. And the other way would be through computing certain complicated functions on a neural network, right? So indeed, there is a comparison to be done. And in fact, to build on this, people are thinking of quantum neural networks, meaning if one can keep the structure of the neural network, instead of computing with the computer, like the various functions, one can insert in certain places maybe a quantum device to compute certain parts in this way that we have seen. So people are really looking at this and computing. I cannot, really say, I don't think there is clear understanding on what is better now, besides the fact that classical computers now are supercomputers and we have few qubits, I think. But people are looking at this comparison, indeed.
Yeah, maybe I can comment on this. There's a whole branch in my group who is looking at quantum machine learning. Okay. And for example, we are looking at Boltzmann machines, the classical Boltzmann machines and the quantum Boltzmann machines. What we experimentally find that it depends a lot of the input data, whether either the classical or the quantum Boltzmann machine works better. And what we are trying to understand here is why this is the case. Why sometimes the quantum Boltzmann machine outperforms the classical Boltzmann machine, and why sometimes it's the opposite. And I think that's really an interesting direction to look at, really to get some experience in this, but also to get some theoretical understanding of this. And we are on the way for that. I find this a very interesting direction.
But would it be, by increasing the complexity, of the problem in a neural network, you still have the exponential dependence on the parameter space, right?
Yeah, but still.
Yeah, but this is something that you won't encounter in the quantum computation.
But at what point? That's the question. And really,
Okay.
if you think of neural networks and quantum Boltzmann machines, you can represent